Okay, this problem is a question that says a 200-gram wood block is firmly attached to a horizontal spring. So here is a wall. Here is the spring. Okay. And the mass of this block is 200 grams or 0.2 kilograms. It also says that the block can slide along the table where the coefficient of friction is 0.4. So mu is 0.4. A force of 20 newtons compresses the spring 18 centimeters. So what we have is basically the spring is compressed now, and if we take this distance and this distance, that distance is a distance of x, and x is equal to 18 centimeters or 0.18 meters. If the spring is released from this position, how far beyond its equilibrium position will it stretch on its first swing? Therefore, what they're asking is they're saying if we let go of this compressed situation, basically this mass is going to end up somewhere over here. But how far? So let's draw a picture of that. And so the question is saying, if the spring is released from this position, how far beyond the equilibrium position will it stretch on the first swing? So here is the equilibrium position again. And so the question is asking, what is this distance? What's this new distance? Okay. So we'll call this x initial, and we'll call this x final. Okay. That's what we're looking for. We're looking for x final. Question mark. Now, we're going to solve this problem using energy, and we're going to say the initial energy is equal to the final energy. There is one little added interesting tidbit in here, and that is there is friction in this problem. You see, there is friction. So let's write down what types of energies we have initially. Initially, there is no gravitational potential energy either in the initial state or in the final state, because it's all at the same height. Do we have any kinetic energy in the initial state? Well, no, because you see at this location here, we've compressed it, but it's at a stop. And so there is no kinetic energy initially here. In this state here, again, the maximum displacement, the final velocity is going to be 0. That's by, definition of it being at its furthest horizontal position. Therefore, we have no kinetic energy before or after it in terms of being initial state and final state. And we have no gravitational potential energy. So the only things we do have are elastic potential energy, initial, okay, equals final elastic potential energy plus, here comes the little added complexity, is the work done to friction, because that energy is gone to heat. So, how much do we have initially? Well, it's 1/2 kx squared initial. And finally, we have 1/2 kx final squared plus the force of friction times the distance it's traveled. So, let's now, what we need to figure out first of all is what's k? Question mark. Now, the equation that we can find k from is f equals kx. And in the problem, initially, we were given that, we didn't actually write that down. It says that a force of 20 newtons. So, in this situation here, a force of 20 newtons was applied in this direction in order to get it to compress this distance, x initial, okay, which we know is 0.18. So let's go ahead and work out k. K is equal to f over x. Yes?
Isn't force of friction applied here?
No, not in this situation, because the question was there force of friction in this, let me change colors here, in this determination of the spring constant, is there any force of friction? Well, you see, force of friction is a reactive force. There would be force of friction on the way to this location, but once this object is stationary, there isn't going to be any force of friction once it's at this location.
But isn't it like thrusting force into that position, so friction is applied?
There would be static friction. But let me read the question again. It says where the coefficient of friction is 0.4. I'm going to now. Let's delve into this a little bit deeper because it's a valid question. If we look at the free body diagram, let me change colors again here. If we look at the free body diagram, let's do it up here. Of this situation here. We've got the 20 Newton force applied this way, and we've got the force of the spring going in the other direction. Okay? Those two forces have to be equal and opposite, such that the net force on that mass is 0. Okay? So what we're going to do is we're going to say, so in this case, really, the net force is 0 on this thing. So we don't need friction. The friction doesn't play a part in determining the spring constant here. Okay, so this force of 20 newtons divided by a distance of 0.18 meters is going to give us 20, enter 0.18 divided by, so we're going to get a spring constant of 111 newtons per meter. That's K. Now we know K. So we can substitute it in here. Remember, what we are looking for here, what's our end goal? It's to find XF, to find the final position beyond equilibrium here. So we could solve for XF. However, there is a little hitch here, and that is, what is D? You see, this D, is it XF? It's not. Is it XI? No. Actually, if we look at the whole situation, if I change colors again, and we start at this location, and we end up here. So D is actually all of that. And mathematically, that would, therefore D would equal xi plus xf. Okay? So we should make a note of that here. D is equal to xi plus xf. And what's our force of friction for that matter? Well, a force of friction is equal to mu Fn, and this is a horizontal flat surface, so Fn is going to equal mg. And so we've pretty much got everything now. We can now solve this equation. All we need to do is put in some algebra. Let's rewrite the equation one last time. Okay, so we've got 1/2 k xi squared is equal to 1/2 k xf squared plus the force of friction, which is mu mg, multiplied by a distance of xi plus xf. Okay, and we're looking to solve for xf. So what I would do here is I would expand this out and put everything on one side of the equation. So rewriting it, 1/2 k xf squared. So I'm just taking this term over there, and then I'm going to go plus mu mg xi plus mu mg xf, and then I've got minus this term here, which is 1/2 k xi squared, and that's all going to equal 0. Now, why did I do that? Why did I set it all equal to 0? Because I recognize this is actually a quadratic. Okay, what are the terms? Well, here is the a term, 1/2 k xf squared. That's the a term. What about the b term? Plus, now there is an xf here. Okay, so that's going to be plus mu mg xf. And now I've got plus, now I'm going to put this in brackets here, mu mg xi minus 1/2 k xi squared equals 0. Therefore, in terms of AB, that's my A, that's my B, and this whole term here is my C in the form of A x squared plus bx plus c equals 0. That's a quadratic. So let's work out what they are. A is going to equal 1/2 of 111 newtons per meter. So that's going to give me 55.6 or 55.55. So 55.6, say. And B is going to give me 0.4 times the mass. Now, the mass, I believe, was, I did all this algebra and I forgot what the mass was. 0.2 kilograms. 0.2. Okay, so 0.2 kilos multiplied by 9.8 newtons per kilogram. This gives me 0.4, enter, 0.2 times, 9.8 times, and I'm getting 0.784. Okay, And the last one, C, is going to equal, okay, so this one's a little longer. 0.4 times 0.2 times 9.8, I'm just not going to bother with units at this point, times xi, which was, I think it was 0.18. Yeah, xi was 0.18. 0.18. And then, so I'm taking this all, by the way, from here. Minus 1/2 times 111 times 0.18 squared. What's all that going to give me? Okay, so 0.4 enter 0.2 times 9.8 times 0.18 times 0.5 enter 111 times 0.18 squared times subtract, and I get a value of negative 1.66. No, because the question was, do one of the distances have to be considered as being negative? No, because the reason is that what we've said initially is that, change colors here again, my initial energy is this much energy, and that's a positive amount of energy. My final energy is this much energy, and that's a positive amount of energy. In fact, it wouldn't even matter if I used a negative distance, because look, I'm actually squaring my positions, and so it's going to be the same value in any case. However, what is important is to notice that for the distance d from here to here, if you happen to use a negative value for, say, xf, you'll get it wrong, because the d is the total distance from your initial point to your final point. And friction, in fact, is dissipated over that entire distance. Okay? So going back to the problem, this is a long problem here. How do you solve this at this point? Yes, you can use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. However, luckily, I have a computer program, or in my calculator, that can solve quadratics. So let me plug in these values for a, 55.6, put that into a, and then 0.784, put that into b, and negative 1.66, and put that into c. And then I will run my program, and my answer ends up being for x is equal to negative 0.18, or it's equal to 0.16. Now I'm going to discard the negative value, and my answer is, well, it's actually 0.66. So there you go. Okay, so my xf is going to be 0.166 meters, or 16.6 centimeters. Long problem, definitely a lot of work. Hope you enjoyed it.